The last two lessons in Chapter 8 both deal with complex numbers in polar form. In 8.8, we'll look at powers of complex numbers. Down below it says, what is the product? If we take r CIS theta and square it, what that means we're doing is we're taking r CIS theta times itself. And the rule for combining or multiplying in polar form is we take our r values and we multiply them together. And then we write CIS. We take our theta values and we add them. This ends up becoming r squared CIS 2 theta. And that's all you do. That's your product. Over on the right, if we raise it to the third power, what that means is we'll take our answer from r CIS theta squared and multiply it by r CIS theta one more time. That would become r squared CIS 2 theta times another r CIS theta, and that would give us r cubed. Notice if we multiply the r values, r squared times r, CIS, and then 2 theta plus theta, that would give us r cubed CIS 3 theta as our product. Notice the connection between the exponent that you're raising it to and the answers that we have pretty consistently within each product. This is known as de Moivre's theorem. De Moivre's theorem will allow you to raise any complex number in polar form to any exponent by applying this definition. That takes the place of having to write it out and multiply the r's together and then add the thetas all together n number of times. So if you have r CIS theta to the nth power, that's the same as r to the nth power CIS n times theta. So this is a definition you're going to want to keep with you. Now the trade-off for this problem, just like in 8.7, is you want your theta values to be between 0 and 360, or between 0 and 2 pi, depending on how the directions are laid out. Because of this, if you ever have an answer that's greater than 360, simply make it coterminal by subtracting 360 however many times it takes to get your theta value within the correct range. If you have an example like z equals 1/2 plus square root 3 over 2i, this is in rectangular form, a plus bi. In order for us to apply de Moivre's theorem and find different exponents, we first have to convert to polar form. Remember, r squared equals a squared plus b squared. And this will be new for us too. This is the first time I think that we've had fractions for a and b. If we square them, we just have to recognize that we square the top and the bottom of that fraction. So we have 1/2 squared plus square root 3 over 2 squared. Well, 1/2 squared is just 1/4. Square the top, square the bottom. Also get this, everybody. If we take square root 3 squared, that's just 3. And then 2 squared is 4. Combining like terms, 1/4 plus 3/4 is 1. And then if we take the square root of each side, r simply equals plus or minus 1. Now off to our theta. By definition, tan theta equals b over a. This should be interesting with those fractions. Tan theta would equal square root 3 over 2 for b divided by 1/2. But when we divide by a fraction, the alternative is to multiply by its reciprocal. That would be square root 3 over 2 times 2 over 1. And the 2's cancel out. Square root 3 divided by 1 is square root 3. And that's unit circle friendly. Oh, so much to remember. Theta equals tan inverse of square root 3. On the unit circle, there are two locations where that's true. Tangents positive in quadrant 1 and in quadrant 3. Our choices for theta then are 60 degrees or 240 degrees. We have to think about which one makes sense for our given z value. 1/2 plus square root 3 over 2i. If we were to draw a quick sketch of where that puts us, 1/2 to the right, up square root 3 over 2, would be somewhere in quadrant 1. Making 60 degrees the correct angle location for our polar coordinate. That makes z in polar form 1 CIS 60 degrees. And we'll use this as our template to find different powers for de Moivre's theorem, or using de Moivre's theorem. Find z, z squared, z cubed, all the way up to z to the 6th power in polar and rectangular form. Now, truth be told, there's not enough space for this to happen. So write small, and I'm sorry. All right, so we have z to the 1st power all the way up to z to the 6th. So we're going to do z squared, z cubed, z to the 4th, 5th, and 6th. Okay, so in polar form, we're going to apply de Moivre's theorem. Remember, that's r to the n cis, and then n times, that's an n, time, n times theta. All right, we'll get that there. Oh, wow. Okay, let's just try that all over again. Sorry, everybody. This doesn't need to be any longer than it's going to be. R to the n cis, here we go, n times theta. Whew, got it. Okay. So z to the 1st power, we just did that one. That's just the one we start with, 1 cis 60. Now z squared is going to be 1 squared cis 2 times 60, which is just 1 cis 120. So that's not so bad either. 1 cubed, and then cis 3 times 60. Well, 1 cubed is still 1. CIS, 3 times 60 is 180. See if you can complete the last 3. Z to the 4th, Z to the 5th, Z to the 6th. Please press pause on the video, fill that out, and then press play, and we'll continue from there and convert to rectangular. You should have 1 CIS 240, 1 CIS 300, and 1 CIS 360. But wait on that. Remember that 360 actually can't be a valid option. So if I subtract 360 from it to be between 0 or 0 greater than or equal to 0 but less than 360, this last number actually becomes 1 CIS 0. And that'll be helpful when we convert to rectangular. You're definitely going to want access to a unit circle as we convert to rectangular form. So make sure you have that, either grab one from a different packet or be willing to flip back and forth to help convert these. Now z to the 1st power, we already know the rectangular form. That was the original z. It's just 1/2 plus square root 3 over 2i. For graphing purposes, that's just going to be 1/2 square root 3 over 2. But that square root makes it even trickier, so I'm going to go one step further and convert the square root to a decimal. We're going to graph 1/2 0.9 on our Argand diagram. So that's the easiest one of them. So we're going to have to try to fit all this into the space provided. All right, for 1 CIS 120, z squared, we now have to calculate that. We'll do 1 cosine 120 plus 1i sine 120. Okay, at 120, cosine equals negative 1/2. So 1 times negative 1/2 is just negative 1/2, not so bad. And then 1 times sine 120, at 120, sine is positive square root 3 over 2. So that becomes square root 3 over 2i. Notice it looks very similar to what we had up above, but the negative, or the negative 1/2 changes the direction. So that's going to be negative 1/2 square root 3 over 2, or 0.9. So again, not awful. The cubed, 1 CIS 180, that becomes 1 cosine 180 plus 1i times sine 180. So over on the left side of the graph at 180, cosine is negative 1. 1 times negative 1 is negative 1. Sine at 180 is 0. That means we have 0i. And our ordered pair for graphing purposes is negative 1, 0. Again, I want you to pause and complete the second half. Do z to the 4th, z to the 5th, z to the 6th, and determine what they would be in rectangular form. Let's see how you did. For z to the 4th power, I got negative 1/2 minus square root 3 over 2i. Z to the 5th power, I got positive 1/2 minus square root 3 over 2i. And then our last one, z to the 6th, I got 1 plus 0i. Our goal now down below is to sketch the graph in both polar form and coordinate form, or in rectangular form on the R-GAN diagram to see if they match. Let's first plot on the polar coordinate system, and we're going to connect the dots when we're done. Now, z to the first power was 1 CIS 60. What I did was I doubled my graph so that every 2 circles is 1 unit, just to make the picture bigger. 1 CIS 60 is going to rotate up to 60 degrees. 1 is that second circle out there, so I'm just going to put a dot there. There's z to the first power. 1 CIS 120 is just going to keep along that circle and go over here at 2 pi over 3. Oops, that's a 60 right there. That looks like a 50, sorry. Oh my goodness, why can't I make that work, everybody? All right, so that's the 60, and then here's the 120. That's where I was trying to go with that. Okay, and then we have 1 CIS 180. That's just on that left-hand side, all the way over here. And we're kind of getting a pattern. 1 CIS 240, that would be down here below. 1 CIS 300, and then 1 CIS 0. Now, if we connect these dots, I'm just going to go straight across, kind of connect it to each of those locations, like so. We form a hexagon, and that's z to the 6th power using Dumont's theorem. On our R-GAN diagram, I'm going to do the same thing. I'm going to double it on the x-axis and the y-axis just to make our shape a little bit bigger. For z to the first power, it's 1/2 0.9, which is going to put us pretty close to 1/2 1 up at the top. And then we go -1/2 0.9, that'll move us to the left. -1 0 right over here. -1 or -1/2 -0.9 drops us down below. So we're starting to kind of see that same idea, that same shape. Then we have +1/2 -0.9. And we end at 1 0 on the right. So again, start at the top. We're going to connect to the left, and then down here to that corner, down into quadrant 3, across into quadrant 4, back up to the origin over here, and then connect it to our original z value. So you can see here that our product in polar form for each of these exponents matches or agrees with our products that we have converted back to rectangular. And that's where we'll stop the video. We'll finish the rest of our notes tomorrow in class.